Hi guys, welcome back to another video. So we're going through the Practical Electronics for Inventors book. I'm learning this at the same time as you are, so let's learn together. I'm currently on the AC chapter. I'm on page 91. And so in the last two videos, we just did some exercises here. So if you want to see those, go back and watch those two videos. So for example, like how much current would flow through a 100 ohm resistor connected across 120 volt 120 volt AC outlet. And it talks about power dissipation. So there's some good questions there. There were 6 of them. So we just finished those. I'm going to carry on reading from here. I actually genuinely feel like I'm making some good progress now. So I'm really enjoying this. And if you watch my last two videos, you know that I've been forgetting to record my iPad screen. And as you can see, I'm recording this time. So all good. I've remembered this time. So yeah, let's get into it. Delete this. Cool. Okay, so measuring RMS voltages and current. There are many digital multimeters that do not measure the RMS value of an AC voltage directly. Often the meter will simply measure the peak value and calculate. That's very clever. So multimeters will just measure the peak value and then calculate RMS from there. Obviously simple enough. Assuming that the measured waveform is a sine wave. True. And then display this value. Analog meters usually measure the half wave average value, but are made to indicate the equivalent RMS. I don't think I've seen an analog multimeter. Oh, I have. Wait, I've seen analog voltage probes. I bought some at the car boot sale. I suppose maybe that's what it means by analog meter. Interesting. Okay. Not something that I necessarily need to. Do I need to learn that? I mean, I've learnt it now, I suppose. I won't take notes on that. I think I'm alright. Analog meters. Okay, read that. True RMS. Let's start highlighting because when I don't highlight, I get lost. Get completely lost. True RMS multimeters, on the other hand, measure the true RMS value of voltages and current. Okay. I mean, maybe there's a use. That's what I assume. There's going to be like very unique, specific use cases for that. But if the calculation works, what's wrong with the calculation? Okay, so they're especially handy. Okay, because if it's a non-sine wave voltage, of course, yes. Though relatively expensive, these meters are worth the price. If you say so, mate. I'd rather get a new CPU. It's important to note that true RMS meters will also include the contribution of any DC voltages or current components present along with the AC. What? It's important to note that true RMS meters will also include the contribution of any DC voltages or current components present along with the AC. Is that like saying that if a circuit has, an AC input plus, a battery supplying some DC voltage, then the RMS becomes the sine wave AC plus the DC? I mean, that would be obvious, right? I would have thought. Fortunately, you can still get a fairly accurate idea of the RMS value of a sine waveform knowing one of the other measurements, such as the half wave average peak or peak to peak. I don't really know what half wave is. We had the relationships. Wait, let's just. So we had this relationship table up here. It didn't mention half wave. All of this, there's no mention of half wave there. But that's okay. This can be done by calculation or using the table in figure 2.89. What? I just looked at this. 2.89. Right, this one. Oh no, 2.8. That's 2.87. 2.89. Where's 2.89? Here. Half wave average. A half wave average is 1. So then it's 0.9, 0.6, 0.3. What? Okay, let's carry on reading because I don't understand what I'm looking at there. As you can see, I can't see. It's also possible to work out the RMS value of a few other symmetrical and regular waveforms such as square and triangular waves, knowing their peak, average, or peak-to-peak values. So if you have peak, average, or peak-to-peak, then you can work out RMS, which we know. An important thing to note when using a table is that you need to know the exact basis on which your meter's measurement is made. For example, if your meter measures the peak value and then calculates and displays the equivalent sine wave RMS, this means you'll need to use the table differently when compared to the situation where the meter really measures the half wave average and calculates the sine wave RMS figure from that. So take care, especially if you're not sure exactly how your meter works. Don't really know what to take away from that. I feel like I didn't really understand that too well, but I also feel like I don't really have to understand that. Who knows? I'm also not sure what we're talking about when we're talking about half wave here. I get what half a wave is. Like I get that this is half a wave, but why are we? Oh, okay. Are we just saying that if you know the top half, if you know the first half of the cycle, then obviously you just invert that across the zero axis, and you have the other half, obviously, right? So if I tell you that we've got a voltage waveform of this, right? What's the other half? Then you just simply take that waveform, duplicate it, spin it around. Hopefully I didn't change the size of it. It definitely changed the size of it. And then yeah, my phone is silent. Why is it dinging off for? Wants to tell me, give me an update about the weather. Love it. Anyways, that's not best I could do. But anyways, yeah. So is that what that's saying? But I don't get how you would deal with that in a number sense. But that's fine. Anyways, like I said, I don't feel like I necessarily need to know that well. So let's crack on. The mains power. Delete this. In the United States, 3 wires run from the pole transformers or underground or surface. So I don't need to know too much about mains for now. For this year's modules. However, I'm firstly studying power electronics next year, but secondly, I actually want to get into power engineering. So I should probably pay attention to this. So let's give myself, it's one of those where it's like, if you procrastinate, or you go into debt, you're just harming your future self. But when you choose to save money, choose not to spend or go into debt, and you don't procrastinate, you're being nice to your future self, which is quite interesting because psychologically, there's I remember seeing some videos about how we don't actually view our future self, as us. We view the future version of Hamid 2021, as some other guy. So we're just like, I'll eat this donut now, and I'll take out the grand debt. Shut up. But yeah, anyways, that's just a little side note. Let's crack on. In the United States, 3 wires run from the pole transformers or underground or surface enclosed transformer. Don't actually know what a transformer is, but okay. I mean, I know it technically, kind of, but don't know what it does. To the main service panel at one's home. One wire is the A phase, usually black in color. Another is the B phase wire, usually black in color. What? Okay, and the third is the neutral wire, white in color. I don't remember seeing this. Obviously, we're talking about United States here. Maybe I should look at the UK alternative. Should we try it? Is it worth our time? That's the question. US versus UK. Black, white, AB wire. AC 240 volts, 120 volts. So let's try and put in some keywords. My wife lived in England for 10 years and loves British kettles. This is when this is funny. This is funny. Like there's this whole issue with kettles, because of the different voltages and how our kettles are amazing. Which is funny because we're English and we're tea drinking guys, so our kettles usually boil a lot faster than American kettles, which is hilarious. Okay, so this guy's not teaching us anything. He's just anyways, he's basically dedicated to rewiring his house for a kettle or rewiring his kitchen. Anyways, um, okay, let's do this. US versus UK mains AC, mains AC. I don't know. Wire colors. So I don't really understand what's been said here. So okay, let's do what we're doing. A phase, B phase. Mains AC, A phase, B phase. You know what? I keep saying this actually, but I keep forgetting to link the guy on my videos. So I apologize. But basically, this guy Electro Boom YouTube. I just give him a shout out because I always keep forgetting to do it. But his videos are absolutely amazing. Honestly, highly recommend. You know, he has some sick videos where he goes, he like does stuff at wall outlets. It's brilliant. It's absolutely brilliant. So he has quite a lot of stuff. Looking like how safe is a shower head of doom. Anyways, continuing on. Mains electricity by country compared B A phase, B phase, C phase. Yeah. Black wire. I mean, this is kind of what makes sense to me, but so I don't know. Yeah, it's too over my level for me to be really even understand what they're saying. I don't know why they're introducing it, but okay, let's just carry on. So they're saying we've got two wires, A phase and B phase. They're both black, and we've got a third wire neutral, which is white. Okay, figure 2.90. Where's that? Here. Oh dear. This he's touching a short, standing on a steel frame. I didn't know about this. I found this interesting. They taught us this earlier in the book about how houses are actually grounded with a grounding rod, which is interesting. All right, let's read this and then hopefully I'll be able to understand that diagram. The figure 2.90 shows where these three wires originate from the pole transformer. Okay, let's have a look at that. The pole transformer. Okay, so you got this mains power line. So they're saying you've got a neutral and here it's talking about three phases. They were only talking about A and B phase, but okay. Okay, yeah, so the transformer is like what's that called? Isolated. You got the mains lines here. Okay, so these are got it. So you got the main three phase power running, across the city. Then you've got, a step down transformer. You've got some residential lines here. And as you can see, they're all breaking off the two phase hot wires, phase A and B. And then you got the neutral wire, and they're coming down into people's houses here. And then obviously all of the houses are grounded. So this grounding here is this grounding rod here. So we've got a phase A 120 volts, phase B 120 volts. Okay, so they're actually out of phase by 180 degrees. Interesting. This is crazy, like if this is the first video that you're watching of mine, of this series, and you're listening to me right now, it probably sounds like I'm quite smart. And I'm really not. Like 8 videos ago, I had no idea what I was just saying right now. That's crazy. You can learn a lot in a few hours. Okay, so here you've got these two hot wires and the neutral wire coming in to this person's whatever it's called, circuit breaker box. So you've got, says phase A and B and the neutral wires. Interesting. So you got the 220 volts coming in here, right? Wow, look at this. So these mains wires are 4 to 16 kilovolts. That's mad. Because if you if you touch 120 volt wire in your house, mate, you're probably, I don't know what, probably it's gonna hurt. But touching one of these, 16,000 from 120 to 16,000. Bloody hell. All right, so crazy that I want to get into power electronics. It's actually, thinking about it now, it's actually very scary. Okay. All right, let's carry on reading. So where was we here? I've ended up getting excited by this drawing. I'm a proper pictures guy, you know. Show me a picture and I love you. So it shows where these three wires originate from the pole transformer. Pole transformer, pole transformer, pole transformer. Okay, here. Yeah. The voltage between the A phase and B phase, or the hot, is 240 volts. Does that mean the peak voltage? I mean, sorry, the peak to peak is 240 volts. While the voltage between a neutral wire and either, nice, is 120. This is actually super interesting, man. I'm pumped about this. Okay, so let me try and take some sort of notes here. I mean, first I should just probably screenshot this picture. This is cool. I definitely would like to have this stuff fully grounded. Use the pun. I like that grounded pun. It's quite interesting. Being an electrical engineer, you can use it for everything. Okay, so we got this picture here. Let's just crop it. Okay, so let's take some notes. So this is US. So really, it'd be good for me to learn the UK version of this. What's the UK? UK, we're not 120 volts, are we? We're 200 and we 230, 240 volts. I don't know. I can't remember now. I think we did it two, 3 videos ago as well. All right, so we'll just take notes on US for now and just get an understanding of US, and then hopefully switching over to UK won't be too hard. So what did we last read? We read that, so mains power, and what we're saying is that you've got three wires that enter the home. So you got A phase, B phase, and neutral. So you got 120 volts, minus 120 volts, and you got 0 volts. So there's a peak to peak of 240 volts. Okay, these voltages are nominal and may vary from region to region, say 117 volts instead of 120 volts. At the home, the three wires from the pole green box transformer are connected through a watt meter and then enter a main service panel that is grounded to a long copper rod driven into the ground or to the steel in the home's foundation. That's another way that they ground it. So they ground it by just connecting it basically to the chassis of the house. Just like how you ground your car's battery into the chassis of the car. Very interesting stuff, you know. You know, if you think about like how much of the world around us has been built by very, very smart people, and we're just piggying off the back of them, even though we have much better lives than they ever did. Like, you think about, my life is way more comfortable than Edison's life would have been, or Tesla's. Amazing, isn't it? Should definitely be grateful. Okay. So I'm interested by the watt meter connection. I assume obviously that watt meter meaning the electric meter to check how much your consumption, right? Or is that to serve as a breaker? I don't know. You got the breakers here. Where's the watt meter? Can you see it? Hot, neutral, ground, split DC power supply, grounded chassis. Um, okay. I can't see a watt meter on here. Neutral, neutral bar, ground bar, and then 240-volt load, ground return, ungrounded lamp, shock hazard. Okay, that's fine. There's no watt meter that I can see here, but I get it if by watt meter they mean, our electric meters that tell us how much usage we used, that would make sense, I think. So the A phase and B phase wires that enter the main panel are connected through a main disconnect breaker. Yeah, that's the breaker box. While the neutral wire is connected to a terminal referred to as the neutral bar neutral bus. A ground bar may also be present within the main service panel. The ground bar is connected to the grounding rod or the foundation steel supports. Got it. Well, regardless, they're just trying to make it so that you have a reference point to 0 volts or to ground, right? Within the main service panel, so maybe I should. Okay, it's okay. So within the main service panel, the neutral bar and the ground bar are connected together. They act as one, of course, yep. However, within sub-panels, service panels that get their power from the main service panel, but which are located some distance from the main service panel. So, for example, if you had a shed at the back of your house, the neutral and ground bars are not joined together. Instead, the sub-panel's ground bar receives a ground wire from the main service panel. Often, the metal conduit that is used to transport the wires from the main service panel to the sub-panel is used as the ground wire. However, for certain critical applications, the ground wire probably will be included within the conduit. Also, if a sub panel, this is to stop like it malfunctioning, right? Also, if a sub panel is not located in the same building as the main panel, a new ground rod typically is used to ground the sub panel. Note that different regions within the United States may use different wiring protocols. Therefore, do not assume, man. When I start working with main stuff, I've got a plug right next to me here, which I cracked when I was pulling it. I tried to pull out, try to pull out an extension cord, but I was doing it from like 4 meters away. I was just like yanking on a wire, hoping the plug would just come out of the wall socket. Obviously, it kind of like just, instead of it coming out normally, it just cracked the whole panel. So I could get my landlord to fix it myself, but I want to do it myself. But this is the problem for me, these assumptions. So, that's going to be a big problem for me. When I start working on main stuff, man, I'm sure it should just be as simple as going downstairs, turning off the electricity, and then taking off the panel, putting a new one on, and undoing the wires and putting them back in. So it should be a simple job, but that's the thing though with me. I'm always assuming, and I don't mind assuming when I'm dealing with a laptop or an Apple iMac or something. You just break it, is what it is. Maybe there's some sparks, maybe you blow up a power supply, but messing about with 240 volts, no thank you. All right, so therefore, do not assume that what we are telling you is standard practice where you live. Contact your local electrical inspector. Within the main, this is interesting, I mean, I get that all of this is not really relevant at all to what I'm trying to learn in my instrumentation and control module or in my electrical and electronics principles 2 module. However, saying that, it's good for me to know, and if you're an electrical engineer, it's probably good for you to know as well. So within the main service panel, there are typically 2 bus bars into which circuit breaker modules are inserted. One of these bus bars is connected to the A phase wire. Hang on a minute, didn't get any of that. Within the main service panel, there are typically 2 bus bars. What's a bus bar? Buses are just like wires, right? But what's a bus bar? Into which a circuit breaker modules are inserted. Okay. Oh, got it. It's just a connection where you've got the A phase and B phase going in, and you're just talking about so a bus bar is like this, right? So they're all like connected, and then you got the A phase wire going in there and B phase wire going in there. I think it's shown here. Yeah, here. Okay. So the power group of 120-volt loads, e.g., upstairs lights and 120-volt outlets, you throw the main breaker to the off position, and then insert a single pole breaker into one of the bus bars. Wow, we're getting deep here. You can choose either the A phase bus bar or the B phase bus bar. The choice of which bus bar you use becomes important only when it comes to balancing the overall load. Ah, interesting, yeah. Obviously, you should all know about load balancing, but I didn't even think about that actually. Next, you take a 120-volt 3-wire cable and connect the cable's black hot wire to the breaker, connect the cable's white neutral wire to the neutral bar, and connect the cable's ground wire, green or bare, to the ground bar. You then run a cable to where the 120-volt loads are located, connected the hot and neutral wires across the load, and fasten the ground wire to the case of the load. Typically, a ground screw is supplied on an outlet mounting or light figure for this purpose. To power other 120-volt loads that use their own breakers, you basically do the same thing you did in the last step. However, to maximize the capacity of the main panel, to supply as much current as possible without overloading the main circuit breaker in the process, it is important to balance the total load current connected to the A phase breakers with the total load current connected to the B phase breakers. This is referred to as balancing the load. Now I understood about 30% of that. But it's cool. Don't worry. Like I said, I'm using this as more of an introduction than me actually learning this, because I'm going to learn this in my third year anyways. Now, if you want to supply power to 240-volt appliances, oven, washers, etc., you need to you insert a double pole breaker between the A phase and B phase. Ah, nice. Okay, so that's why on breaker boxes, I don't know if you guys have looked inside one, but you'll have ones that are like unique. They're not connected. These are double pole breakers. Okay. So they're connected between the A phase and B phase bars in the main. Next, you take a 240-volt 3-wire cable and attach one of its hot wires to the A phase terminal of the breaker and attach its other hot wire to the B phase terminal of the breaker. The ground wire is connected to the ground bar. You run the cable to where the 240-volt loads are located and attach the wires to the corresponding terminal of the load. Also, 120-volt, 240-volt appliances are wired in similar manner, except you use a 4-wire cable that contains an additional neutral wire that is joined at a neutral bar within the main panel. In addition, in many places, modifications to mains wires must be carried out or checked by a certified electrician. Yes, let me keep that in mind. As a note of caution, do not attempt home wiring unless you are sure of your abilities. This is true. This is true. If you feel that you are capable, just make sure to flip the main breaker off before you start work with the main service panel. When working on light fixtures, switches, and outlets that are connected to an individual breaker, tag the breaker with tape so that you don't mistakenly flip the wrong breaker when you go back to test your connections. Okay, so yeah, I wouldn't say that I understood loads of that, but you know, is what it is. Let's call it a brief introduction. Capacitors. Okay, so this is gonna get deep now. This is actually my first time learning about capacitors. Now, I've had like 2 lectures on them, but I didn't understand anything, and in fact, my brain switched off after 30 seconds. So we'll pick up this on the next video, and I'm excited to learn about capacitors. So, all right, guys, thanks for watching. What did we even do in this video? I don't really know what we did. What did we do? We went through kind of like mains, right? Mains power, and then we read something previously up here about RMS. Okay, so we basically did like measuring multimeters and digital and analog. So it's like a note on measuring RMS voltages and currents, and then a brief look into mains power. Hopefully it was useful to you. I learned a fair bit, in particular from this. and I'm excited to go into and learn this stuff third year. I look forward to that. And yeah, alright guys, thanks for watching, and in the next video I'm excited for this one. Let's get into capacitors. Cool, see you in the next one. Peace.